We have discussed on Fibonacci sequence and the modeling of Fibonacci sequence and Fibonacci matrix with Microsoft Excel. Today, I'm going to introduce the Gershgorin circle, which can be used for analyzing Fibonacci sequence. The Gershgorin circle theorem is one of the important theorem to figure out the size of the largest eigenvalue of the given matrix. Okay, we start with a matrix, n by n matrix, complex n by n matrix with entries aij, and we define R's of I as the ith deleted low sum, which is the summation of absolute value of aij from I equal 1 to n, except I is equal to j. So this is the sum of the absolute value of the entries in the ith row except the diagonal entry. We call this Ri or Ri prime as the ith deleted low sum. Then let D of A's of I and R's of I. This is a closed disk centered at 0 AII and with radius Ri. Okay, if A is a complex n by n matrix, then D of A's of I and Ri is a closed disk centered at the complex number aii with the radius Ri, ith deleted low sum. Such a disk is called a Gershgorin disk. The theorem says every eigenvalue of A lies within at least one of the Gershgorin disk. Okay? Every eigenvalue of A lies in one of the, at least one of the Gershgorin disk. Here is the proof. This, okay, the proof is very simple and clear that you're going to see in the midterm examination. Let lambda is an eigenvalue of A and x is a corresponding eigenvector. Then we can write Ax is equal to lambda x and x is a non-zero vector. And we can choose I such that x, absolute value of xi is the maximum of among the absolute value of xj's from I, j equal 1 to n. Okay? Then this is the largest, so xi is the largest in absolute value number in the vector. Among these xi's, this x1 to xn, this xi has the largest absolute value. Okay? Okay, so absolute value of xi should be positive. If not, if the largest one is equal to 0, absolute value is 0, then means all others are zeros. That means x gotta be a zero vector. It occurs a contradiction. So this largest, if x is not a non-zero vector, then absolute value of the xi, which is the largest absolute value number in x, that is, it should be positive. Okay. Since x is an n-dimensional vector and ax is equal to lambda x, for all I, we can find this equality. Okay, ax and lambda x, those are two vectors. This is one vector, this is another vector. So each I, the first component should be same as the first component of this vector, and second component of this it should be same as second component of this, which is lambda x2. Okay, the third component of this vector is same as lambda x3. So we have this for all i's. Okay, then we can move xi to from left to right. We can move one term to here. So we can write in this way. Okay, and we know this absolute value of xi is positive. So we can divide. We can divide both sides by absolute value of xi after we took an absolute value on both sides. Okay, then lambda minus absolute value of lambda minus aii should be same as this value over xi with the absolute value over it. Next, since we choose absolute value of xi is bigger than any others, absolute value of xj's. So we know this xj over xi absolute value is always less than or equal to 1. Okay? So this we can take it off with the inequality in here. So from here, with this fact, we can have this inequality. So this side, left hand side is less than or equal to summation of absolute value of aij from j is equal to 1 to n except I. This is the ith deleted low sum from the definition. You know what this means? This is the eigenvalue, lambda. Lambda is the eigenvalue. And this is the, this lambda satisfies this inequality. What that means is, if we draw a circle, a disk, with the center, the aii, with the radius ri, then lambda should be inside of that disk. This shows the location. This gives us a criteria to tell the location of eigenvalue. This eigenvalue lambda should be in one of the circle with the center at aii and with radius r of I. This is a Gershgorin circle theorem. Okay. This was shown in early 1930s, but the related theorem was proved more than 30 years before, in 19th century. But Gershgorin understood this theorem in terms of the location of the eigenvalues. That was a very smart idea. From here, we can if we have a matrix, then we can easily draw the Gershgorin disks. Okay, and we can tell that every eigenvalue lambda belongs to one of these Gershgorin disk. Here is the corollary. Eigenvalue of A must also lie within the Gershgorin disks Cj corresponding to the columns of A, because eigenvalue of A and eigenvalue of A transpose are same. So we can adopt the same algorithm for row, the columns instead of row, by taking the same proof of the theorem to the A transpose. If we go to the Wikipedia site, then you will see more information and references on Gershgorin circle theorems. Here, statement and proof and discussions and applications, etc. If this is a complex matrix, then this AI then center that AII. This is right. This center, centers should be AII. That could be a complex number. Okay, that's right. Okay, we can go further, and there are some references that you may. There's some references. Gershgorin's paper on 1931, and the other related works by Richard Varga and Jean Golub and many others. This Gershgorin circle theorem gave the whole new area of research on the location of eigenvalues. Okay, here is an application. This Gershgorin circle theorem is useful in solving matrix equation of the form AX is equal to B when A is a matrix with a large condition number. Okay, and it would be good to reduce the condition number of A. This can be done by preconditioning a matrix P such that P is roughly close to A inverse. If it can be constructed, then the equation PAX is equal to PB can be easily solved for X. Okay, if P is approximation to A inverse, then when you multiply P and A, it is almost the same as the identity. That means X is an approximation. X is equal to PB is an approximation for the system of the linear system of equation AX is equal to B. So you can easily find the approximation of the solution by just multiplying that P to the vector B. Okay, so PA is an approximation of the identity matrix, where the I is the identity matrix. Then the eigenvalue of PA. Think about the eigenvalue of PA. What you can think of. This is the PA. If PA is very close to identity matrix, then the eigenvalue of this PA should be very close to 1, because the eigenvalues of identity matrix are all 1s. So by the Gershgorin circle theorem, every eigenvalue of PA lies within a known area, and so we can form a rough estimate of how good our choice of P was. Okay, so when you choose, after we choose P, then we can just check the eigenvalues of PA by drawing the Gershgorin circles, and then we can check whether it is a good choice or not. Okay, so there are many applications, and also there are many generalization of this Gershgorin theorem. One of the striking facts was discovered by woman mathematician at Caltech. I will tell you more about it later. Example: use the Gershgorin circle theorem to estimate the eigenvalue of this matrix. Okay, what we can tell is all eigenvalues of this matrix are located in the union of these four circles, which was made with these entries. First one, centered at 10, and radius is absolute value of -1 plus absolute value of 1, which is 2. So this is one circle with radius 2 and centered at 10. The second circle is centered at A22, and the radius is the addition of these three positive numbers, 0.6. And third circle is centered at 2, A33, and radius is 1, 2, 3. Fourth circle is the centered at -11, and the radius is absolute value of these three numbers, which is 3. So you can easily draw the graph. I draw the four circles, and we can tell clearly 4 eigenvalues are in the union of these 4 circles. You may see some more information on Gershgorin circle theorem, which was written by me on this web address. So here is some histories and the matrep command, mathematical matrep command, and it shows the Gershgorin circles, and here that shows the eigenvalues are inside of one of those circles. Okay, and the conclusions. And next information is we made it in an English version of those Gershgorin theorems, and that has the matrep command and the simulation and Java applet as well. And here you will see, if we put a matrix of 10 by 10 random matrix like that, then we can choose a special type of matrices, and we can draw the Gershgorin circles. Draw the circles. We can draw the random matrices, and we can draw the Gershgorin circles. Here are 10 eigenvalues because of the 10 by 10 matrix. Then you can see the 10 eigenvalues are here and there, which are the complex numbers, and those are all in the union of these 10 Gershgorin circles. Okay, we can draw it with the Gershgorin circle corresponding to the rows, and we can draw the Gershgorin circles for columns. And also, this is the generalization of the Gershgorin circles, and we can choose the parameters as for the Ostrowski, to find the Ostrowski region, which is a generalization of the Gershgorin circles. And there are many things were done in it, and you can also find those Java tool in here. For example, if we have 14 by 14 matrix, then we can choose the random matrix, then we can draw the Gershgorin circles, and so you will see where the eigenvalues are located. Okay? Those are web address. Okay, I'm going to explain how those Gershgorin circle theorem is related to the Fibonacci sequence. Think about it. In the Fibonacci sequence, we can generalize the Fibonacci sequence with the parameters u and v in here. Then we can formulate in a matrix form with this matrix 0, 1, u, v. So if we multiply this matrix on F1, F2, then it will be changed to F2, F3, and if we square if we do square, then it will go to F3 and F4, and n minus 1 square makes to Fn plus 1, Fn plus 2, like that. Okay? Here. So we can formulate, we have seen the change of ratio to the nth term of f of this sequence is depend on the largest eigenvalues. That's what we saw in the earlier simulation. So for the eigenvalue, the largest eigenvalue of this matrix 0, 1 UV is will give the answer for the growth rate. We can find it from the quadratic formula by using the quadratic formula to find the two eigenvalues of this matrix. Okay, and we see this the increasing ratio will converge to these lambdas. Okay, if you use, I will show you the Excel files and which was made for this simulation. For this, if we choose U and V of these numbers, then as n goes and increase, the sequence increases in this way, and the ratio of increasing and moves and converges and to this number, and which is the largest eigenvalue of this matrix. So if we give the scroll bar to control this U and V, then it will be we will see the interesting we will see the interesting fact. Okay, you see here when U and V are given as 3.88 and 3.36, we will see that this ratio converges to the largest eigenvalue of it. If we change it, okay, we can see view to us a little, make it a little smaller so we can see all changes. Okay, from here, if we change this U, then you see how this largest eigenvalue changes, and also where the change of this number that this sequence converges. You see how it changes when it moves. It makes change the center of this Gershgorin disk, and when you change this, it makes a change on the radius of these Gershgorin circles. Do you see? When the U getting bigger, this radius are going larger, and when V changes, then the center of the radius been moved. Okay, but the eigenvalues are changes, and that's the number, and the sequence converges. This is what this simulation shows. So this Gershgorin circle theorem also were used in the analysis of the Fibonacci sequence in terms of the generalized Fibonacci sequence and matrix like this. Okay, any questions on this?